Okay, so you're working on a homework assignment now that involves a really simplified structure, a structure that's just kind of two rigid bars, a spring at their connecting the two of them, and it's being pushed on. And you kind of know what's going to happen. You know that at some point it's going to deflect upward and form some sort of triangular-like shape. And we've been talking since the beginning of the semester about energy, potential energy, strain energy, work. And what we learned is that for systems in which we can write, for instance, the energy of the system, such that the total potential energy, say for the problem that you're working on in your homework, we know that the total potential energy is going to be a function of, let's say, two things. The total potential energy is going to be a function of the force that we're applying and the angle of rotation, right, of those kind of bars with the horizontal. So we can call that theta. And you can kind of elaborate on that and say, well, our strain energy is going to be a function of theta, and our potential, oops, I should use F there. We'll go with work, so I'll make it a negative sign. My work is going to be a function of P and maybe angle. And we know that this is important if we can identify this, because derivatives of our total potential energy tell us things. The first derivative of our total potential energy with respect to the degree of freedom, in this case, P is imposed and theta is the kind of free degree that this thing can deform in. So the derivative of our total potential energy with respect to our degree of freedom, set equal to 0, gives us equilibrium. And we know that the second derivative of our total potential energy, the sign of this thing, tells us about stability. And then last class, we introduced an entirely different branch of mathematics. And you might be wondering why. And the reason is, for a continuous structure, it's not quite this simple. So this would be for, let's see here. For a continuous structure, things change. So for instance, if I pull on or twist or bend a continuous structure, every material point in that continuous structure might deform a little bit. So if here's my bar, you can imagine kind of speckling this thing with dots and stretching it and trying to see how those dots will either move further apart or get closer together, depending on which loads I'm applying there. And those dots that you've speckled on here depend on their position, right? So if I have a dot that's over near my fingers over here, where I'm holding it, well, some of these dots can't move at all because I'm literally preventing it, I'm clamping it, I'm applying a constraint at that edge saying, you can't move. But in the middle here, these dots are free to deform. So we're interested in understanding how the force that we're applying causes a deformation. In this case, it'll be the kind of the changing of the spaces between those imaginary dots in this material. But we know that depending on where you are in this structure, those displacements are going to be different. For instance, at a clamped edge, the displacement is going to be 0. Over here, the displacement is going to be some amount dictated by how much force we're applying. And this presents a problem for us. And I'll just show it very quickly. The problem is our total potential energy depends on let's say we'll look at a displacement vector, u. So let me define a displacement vector u, which we could think of as having components of u, v, and w. This is typically u reflects this, the non-vector u, the component u usually is used to reflect displacement in the x direction. Let me write that more clearly. Displacement in x y and z. We'll use this a lot, so this is important to keep track of. We're gonna use this notation of saying I have a displacement vector. We'll call it u with the vector notation over it, and it's gonna have three components: displacement in x, y, and z. We'll call it displacement in x, little u; displacement in y, little v; and displacement in z, w. We've already been using this notation, but I haven't kind of explicitly specified it. And so the problem here is that our total potential energy will depend on my displacement vector, which depends on where you are in the bar. This depends on x, y, and z. And it might also depend on your load. That load could be applied at different places. We don't have to care about that for right now, because this is enough to make the problem complicated. So here you can see the difference. In that first problem, the problem that you're currently working on for your homework, the load is fixed in place. The angle is the angular rotation at one point. It's saying, okay, I have this bar, I'm going to measure the angle at that bar, makes the horizon, and that's all I care about. For most continuous elastic structures, our total potential energy depends on displacement, and displacement depends on position. So last class we introduced the idea of an action, and we introduced the idea of a functional. A functional is a function of a variable. So in this first set of problems, we can use ordinary calculus, because all we're dealing with are a function of a variable, function of two variables, function of two variables. But here we have a function of a variable. Sorry, I said it wrong. A function of a variable. Function of a variable. Different math. We introduced the calculus variations by trying to minimize an action. For the most part, for this class for structural mechanics, we're going to typically deal with total potential energy. We're going to deal with ignoring inertia, ignoring dynamics, and just focusing on total potential energy. But the point I'm trying to make here is that total potential energy on its own is a functional. It's a function of displacement, which is a function of position. The displacement in your elastic body depends on which point you're looking at in your elastic body. So this is a functional. Continuous structures, their total potential energy generally takes this form. Here, we can use calculus. And by calculus, I mean we're using calculus to minimize the total potential energy and calculus to check for stability. Here, we need the calculus of variations. Now, you've already been sort of introduced to this most likely in mechanics 1 or statics. And you were introduced to this with the idea of, in particle mechanics, it's perfectly acceptable for you to kind of imagine a pretend displacement of that particle, as long as that particle is free to move. So if the particle is fixed in space, it's fixed. If the particle is free, you can imagine an arbitrary virtual displacement. This is probably ringing a bell, where you can, if you have a virtual displacement, if you multiply that virtual displacement by the forces in that direction. So for instance, you have a particle here, and it's in Cartesian space. We could imagine perturbing that thing and asking it to move in, say, the x direction. Not actually moving in the x direction, but just imagining what would happen if it moves in the x direction. And that would give it a virtual displacement of delta u. I don't know if this notation is ringing a bell. I hope it is. If not, I'll try to make it clear in a second. Again, you can imagine this having a virtual displacement in y or z, which would give it a delta u, a delta v, a delta w. These are fake displacements of this particle. And if we have these virtual displacements, if we multiply them by if we sum over the forces in those directions, we get a virtual work, right? So if I take, for instance, the sum of all the forces in the x direction times the virtual displacement in the x direction, delta u, and set that equal to 0, or I should say, yeah, we can do that. That would be the virtual work in that x direction. We can do that for all three of them. We can take the sum of the forces in y, these are the virtual work of being done on this particle. And we know, or hopefully you recall, that the principle of virtual work says that this virtual work here, the three equations I've listed here, must vanish if the particle is in equilibrium. Is this familiar? Is this stuff you've seen before? Okay, cool. This is the same exact idea that we did last class. This is the same thing where I said, oh, there's an arbitrary function eta that we use to say, pretend we know what the trajectory of our ball is. And since it's arbitrary and not 0, well, whatever it multiplies has to vanish in order for that total action to disappear, to be equal to 0. That's exactly what we did last class. This is the exact same concept. It's just that last class, when we're dealing with trajectories, we ended up with a kind of the more general form, thinking about least action. Principle of virtual work is saying the work must vanish, which leads us to the principle of minimal potential energy, which says that if there's no kinetic energy, then we don't have to think about the action. We can just say the structure, the shape of the structure will be found by minimizing the total potential energy. The total potential energy is a functional. To minimize a functional, we need the calculus of variations. which is what we learned last class. So how do we connect what we're doing when we're throwing a ball up in the air to stuff that's more relevant to us, which is the deprivation of a structure? It starts with these ideas of virtual displacements. And let me connect the notation here because it looks a little weird, right? Like I didn't introduce anything with this delta symbol last class. So how do we get from what I was talking about last class to what we're seeing here? Well, let me show you. So we already know that the displacement vector or displacement field of our structure has components in, say, the 3 cardinal directions, x, y, and z. Well, we can take that displacement vector and we can add to it a virtual displacement. U is some arbitrary function, right? If, like, imagine I pull on this thing in some crazy way. The displacement of this object, maybe it's linear, maybe it's quadratic from the edge to one edge to the other, but it's some function of position. Over here, it's clearly 0. Over on my right hand, it's clearly not 0. There's some function connecting those two. So my actual displacement of this object is a function of, in this case, x, y, and z. But if we pull on in one direction, we'll just say x. So the actual displacement is a function of x. Last class, what we said is, we don't know the actual trajectory of my ball. So what I'm going to do is assume that there's some trajectory, add to that some kind of fake arbitrary trajectory, right? That was where we added eta to it. And then we use that to minimize our action. We're going to do the exact same thing. I'm going to take a little bit more care to say that what we did last class is we took the trajectory that we wanted. We took something like x and we added to that eta, which is some function of time. More carefully, what we would actually say is that there is some let's see here, displacement, the true displacement, we'll call it theta, u naught. This is the actual thing. We're going to add to that some arbitrary function. This is going to be a different displacement field. We'll call it v. Last class, we said that perturbation, or that small thing we added to it, was small. We're just going to have this be slightly away from what we expect it to be. The way you actually do that mathematically is you say, I'm going to add a function to it, and I'm going to multiply that function by a small number. And that small number in all of this, either on the math side or the mechanics side, is usually denoted with the one of the Greek versions of epsilon. This is, if you ever are encountering structural mechanics stuff, they'll use epsilon in 2 different ways. When you see it written like this, it usually means small parameter, small number. You probably are also used to seeing it like this, which looks like a backwards 3, and that's usually what we use to think about for strain. It's confusing, but I will just kind of clarify. This typically represents strain. This typically represents small number. Arbitrarily small number multiplying my function. We're going to do a little bit of math for a second. The end result of that is going to be a much simpler way to keep track of these variations. So we're going to do a little derivation here. And then I'll show you kind of the more modern framework that connects us from this stuff to what I've highlighted up here in yellow. Okay, so what does that look like? Well, we can pretend, to figure this out, we can pretend that we know that our total potential energy is just a function of, instead of being a function of x, y, and z, we'll say it's only going to, the deflection of my bar for instance, is only going to vary in x. So all we care about is the location of material points along the long axis of my bar. So we'll say that it depends on x. And then we'll say, we know from up here that it should depend on, oops, there we go, x, and then our displacement vector. So we'll say that it also depends on u of x. And because these problems typically also depend a little bit on changes in our displacement, I'll show, and because it helps us kind of see how this math connects, it'll make more sense a little bit why I'm including this term. But I'm also going to tell you that my total potential energy might depend on the first derivative of u of x, where this is defined for the ordinary derivative of u of x with respect to x. So I'm just using a shorthand notation for the first derivative with u prime. Okay, so going back to what we did last class, we have the total potential energy. It depends on some stuff. In this case, it's the displacement field, the rate of change of the displacement field, and then just one cardinal direction, the x direction. We need to perturb this. We need to kind of add a virtual displacement to our displacement fields and a virtual slope, if you will, to this thing here. So what does that look like? Remember, last class we said something like we were looking at our action minus the true action, and that gave us, oops, the first variation of our action. What we're going to do now is something very, very similar. Our action's a functional, a total potential energy is a functional. So what we're going to do now is we're going to say, I'm going to take my, I should have called that B prime. Okay, we're going to call that B prime. So it's our B bar. Let's go over here and add a bar on top of this B. This is the true potential energy. So we're going to do that exact same thing here. We're going to take some difference in the total potential energy. We're going to eventually have this equal the first variation of our total potential energy. But because we've introduced this epsilon term here, we have to take an additional step. So what we're going to do is we're going to say, first we're going to get this feels very calculus-y, right? First we're going to have a change in our total potential energy, and then the first variation will be when we take the limit as epsilon goes to 0 of delta F. Oops, not F, delta V. Same idea though. We're trying to get here by looking at the difference between our true potential energy and our perturbed potential energy. This is our true potential energy. Our perturbed potential energy looks like that. What did I do? It looks kind of awful, but it's really not that bad, I don't think. I hope. Let me just point out what we did. We perturbed the displacement fields. We took U, and we said, let's add to it a small number multiplying a different arbitrary displacement field. We'll take our slope, we'll take it and add to it a small number multiplying an arbitrary slope. Same exact stuff we did last class, just more structural related now, right? We perturbed this thing. In last class, we didn't have any of this stuff. We just had one thing we were perturbing. You'll notice that I didn't perturb the coordinate system here. This is 99 times out of 100 the way you would handle a problem like this. There are certain exceptions where you might perturb x, but they're rare. We don't need to worry about them for right now. So for the most part, when you perturb the total potential energy, you leave the coordinate system alone and you perturb the fields, the displacement fields. So our delta V is simply V minus V bar, which is equal to some function x u plus epsilon v u prime plus epsilon v minus u, I'm sorry, f x u and u prime. You'll notice that I shorthanded my notation a little bit here. I hope that's okay. What I did is I dropped the fact that these are functions of x, just for the sake of not having this thing be a million miles long. But u and v are functions of x. They are vectors. Epsilon is a scalar. It's just a number, a small number. We're doing the same thing we did last time. We took a functional. Last time it was an action, which depends on some trajectory. We perturbed that trajectory by adding a small function to it. Same thing here. We're taking a total potential energy, which is a functional. In this case, it doesn't depend on a trajectory. It depends on a displacement field. And then we've also said it maybe it depends on first derivatives of our displacement field. We perturb those displacement field and the first derivative of our displacement field by just adding a small function to it. The function is made to ensure that it's small by having an epsilon term there. You might remember last class what we did for something like this, where we just had some arbitrary function. We don't know what it is. We don't know what any of this stuff is in here. Is we said, well, whenever you have a function like this, where you have one thing, and then you have another thing that's small, you can do a Taylor series expansion about that small thing. Our small thing here is our epsilon v term. So we're going to do a Taylor series expansion in two variables. One is for u and one is for u prime. Sounds miserable? It's not that bad. So let's do that really quickly. We're going to do a series expansion hold on, let me just write this down more clearly. Epsilon is small. Therefore, let's do a Taylor series in u and u prime. So if we want to do a Taylor series expansion in u and u prime, we did this last class. We would say that this whole thing is going to equal, the first order is going to be f of x, u and u prime, right? Because the first order of your Taylor expansion about your small parameter epsilon is when epsilon is exactly equal to 0. So pretty simple. The first term, you just literally set epsilon equals 0, and you get a really simple output. The second term is going to be epsilon times v. Times the first derivative of our function with respect to u. And then we have to do this again. Epsilon times v prime times the first derivative of our function with respect to u prime. So let me just show you, these things are connected. Here, this is the actual displacement. And then this term here is the function we added to the actual displacement. This is the actual kind of slope in the x-axis. This is the perturbation that we added to the actual slope. Both of these are like 1 over 1 factorial. So just 1. We can keep going. We did this last class too. We end up with epsilon v squared over 2 factorial times the second derivative of f with respect to u squared same thing. I'm going to write this. Just give me a second here. I'm going to write this more clearly. This is u prime, and that's the second derivative with respect to u prime. However, we're not done. Second derivatives have a cross term, right? So we could do v u, or we can do this mixed term. We could keep going, but that would be painful. This might already be painful. And then we have to remember that we had that term that was up there already. I'll highlight it for you in a second. This term oops. Give me 1 second. Sorry, this thing is supposed to be minus. This term is just this term. Give me a second and I'll try to explain what we've done here. This whole mess here is the Taylor series expansion. It's in 2 variables. If this isn't ringing a bell, 2 things. One, that's okay. This is just the derivation that's going to get us to what we can actually use more simply. So as much as it breaks my heart to say this, you don't need to be able to crank this out on some random Tuesday night. 2, if you're kind of like, I want to be able to do this, or I want to be able to use this, how do I check myself? Mathematica is your friend. If you put in f as a function of these variables and you ask to do a series expansion about these 2 things, it'll spit out this exact thing. I'll try to cook up a quick little Mathematica notebook to post on the website just for Taylor series expansion so you can see it, because I don't know, it might be useful if you want to be able to do this. But look, our life gets simpler immediately. So why does our life get simpler? Our life gets simpler because, look, this term, epsilon, oh, I don't want to use orange. Let's use a different color. Shoot, use gray. This term clearly has an epsilon squared, right? Because of the epsilon v, epsilon squared, This term that's in green clearly cancels out with the first order term in my Taylor series expansion. They're exactly the same. And so to first order, and first order is all we care about for the first variation. The first variation is, you should think of it as being analogous to the first derivative. And you'll see why it's not exactly the first derivative in like 2 seconds. So at first order, in terms of changing for the virtual work we've done to our bar, we can ignore all the gray terms. The green terms cancel out. And we're left with a not so terrible expression, which is that delta V is equal to epsilon V times the first derivative of f with respect to u plus epsilon V prime as the first derivative of f with respect to u prime. Now, just to remind you of where we are, I said we want to get here. We want the first variation. But in order to do that, we have to take the limit as our small parameter, which is arbitrarily some small number. We kind of know instinctually that our problem shouldn't depend on our choice of epsilon. Like we're just saying that it's a small arbitrary difference. In reality, we're saying it doesn't matter how small. So we should really be able to take this to the limit of epsilon being as small as possible. Once we take that limit, we'll get our first variation of our total potential energy. I kind of sugar-coated that, what that limit looks like. The true limit looks like this. The first variation of our total potential energy is going to be, we can factor out this epsilon times the limit as epsilon goes to 0 of our delta V, and it's actually divided by epsilon here. And this looks like this. Epsilon times delta F, delta U times V, plus delta F, delta U prime, times V prime. And we'll introduce the notation that connects all the dots for you, which is that delta of whatever, so we'll say delta V is equal to, well, let me do this in a different way. This is not how you would see it. How you would see it is delta U is epsilon times V, and delta U prime is epsilon times V prime. You can imagine keeping going. Delta U double prime would be epsilon V double prime. But the end result of all of this, using this, we can kind of connect the dots here. Epsilon V. We'll say that the first variation of V, which depends on X, U, and U prime, is equal to the first derivative. Oops, did I say F up here? Oh, yeah, that's right. No, that's fine. The first derivative of our total potential energy with respect to U times the virtual displacement in U times plus the first derivative of our total potential energy with respect to U prime times the virtual work done to U prime. There's a couple things I want to point out to you. It's all right. So we just did a bunch of math. Let me back up. Let me back up. We need to minimize our total potential energy to find the shape of our structure. Our total potential energy is functional. So in order to minimize the functional, what we need to do is we need to apply a virtual displacement to all the material points. And then we're going to use that virtual displacement as our way of minimizing it, just like we did last class. We just went through the process of showing you what the first variation looks like. And you can kind of see that the first variation of your functional is sort of like a first derivative, right? Here's my first variation. It's like a first derivative. But the problem is twofold. One, it's the first derivative times our virtual work. Now we know from statics that if we're in equilibrium, our virtual work has to vanish. And two, and this is the second subtlety, the first variation includes all the first derivatives that our functional depends on. So in this case, we said our total potential energy depends on displacement and a derivative of displacement. And so we ended up with first derivative of v with respect to displacement, first derivative of v with respect to derivative of displacement. Each of them times their respective virtual displacements or virtual, this is not a displacement, but you get the idea. The reason why I'm bringing this last point up and the reason why I am specifically writing this here is because, for instance, for a bending problem, you might find that for a bending problem, for example, V might depend on W, W prime, and W double prime. W double prime would be the curvature of the beam along X. W prime would be the slope of the beam along X, and W would be the displacement of the beam along X. In that case, take a second and see if you can write down what the first variation of that total potential energy is. You don't need to do anything up here. You just need to basically look at what this tells us in the box. Take a second. It shouldn't be that hard. Hopefully, what you got is good. It's not bad. The math is highlighted just to prove to you that this is why it happens. What I need you to be able to do is this last part. Identify the total potential energy and be able to calculate the first variation of our total potential energy. This is going to help us in a couple of ways. It helps us, one, derive the equations we need to solve. And I'm going to show you that in like 5 or 10 minutes. Two, it helps us use a variety of simplified approximate methods that we're going to learn about coming forward, where what we do is we basically say, all right, I know how the potential energy should look. I know that stretching goes as EA times strength squared, and bending goes as EI times curvature squared. And we're going to say, I'm going to guess the shape of my deformed object with some arbitrary displacements in there. And we're going to use this exact thing here as a way to calculate our approximate deformation of our shape. So this process here of calculating this is going to come in handy for us in a couple of different ways. I've just talked a lot. I know that there was a bunch of math in there that may or may not be familiar. What questions do you have for me?
All right, so like just to clarify, like when we approach a problem, we don't have to do any of all that at the top as long as we know the box.
Yeah, so the question for folks at home was like, do we need to know all the stuff above the box? And the answer is no. You should think of this as like a proof. So, all right, we need to minimize this energy. I'm going to prove to you that the first variation is this. If I just wrote the box thing down, it's kind of a weird thing, right? I have a derivative and then I'm multiplying the derivative by a virtual displacement, which might make sense, but I feel like people will get really tripped up when you start multiplying derivatives by a virtual slope and a virtual curvature. This is just a proof. Exactly right. You don't need to know how to do this. But I will point out that all we really did was took a vector field, added a vector field to it, and then did a Taylor series expansion. That looks messy when you write it out like this, but it's actually kind of turning the crank a little bit of like, there's kind of like 3 methods in applied math that if you can go back and like let them sink in, they'll pay dividends for you for a long time. 1 is Taylor series expansions, 2 is integration by parts, and 3 is the kind of divergence theorem, Stokes theorem, Green's theorem, whatever variant you probably have learned in like Calc 3 or something. Those are the 3 things that in mechanics come up all the time, like all the time. If you just get comfortable with cranking out a Taylor series expansion, there's a lot of magic you can do. So yeah, you don't need to know anything above this box in terms of implementing it on a day-to-day basis. It's just the proof that this is the first variation. And the reason why we care about the thing in the box is that if the thing in the box equals 0, we're in equilibrium. And the nice thing is that this same approach gets us our second variation, which we're not going to talk about too much in this class because it's usually complicated. But so let me just write here. This tells us equilibrium. The second variation tells us about stability. And based on what you saw in the box, you can guess the second variation. The second variation looks like this. Second derivative of v with respect to u plus second derivative of u prime and then I think you'll have a cross term. So it'll be second derivative of v with respect to u and u prime times delta u prime. Yeah, I didn't really do anything. I just said take the derivative with respect to the independent variables. But yeah, the important thing is the thing in the box. And what we're going to do now that we have this thing in the box is do probably like the simplest. Last class we did the simplest variational calculus problem in mechanics. which is what happens when you throw a ball up in the air and you get F equals ma. This class we're going to do perhaps the simplest structural mechanics problem with a variational approach, which is going to be what happens if you take a bar and you pull on it. And we'll show you how to work through all that process. One of the main takeaways I want you to have from all of this is that I feel like I've done a poor job in the past teaching this because I think people associate calculus variations with an action. And I want you to associate calculus variations with a functional. And that functional can be anything. Last class it was an action. This class it's a total potential energy. You can use the calculus, not you can. If you want to for instance, determine the shortest distance between 2 points, you can use the calculus of variations to do that. That might seem trivial. It's a line. It's a line in flat space, but what's the shortest distance between 2 points marked on the back of an elephant? Well, you have, if you're, where do you go to find that? You have to find, there's going to be a curve that's going to be the shortest distance between those 2 points. Or if you're going to fly from London to Sydney, Australia, what does a straight line mean? A straight line means a great circle. How do you know that that's the shortest distance? You use calculus variations to prove that. If you go to the Boston Museum of Science, there's a nice exhibit on a really classical problem that was kind of at the brought up at the time where calculus variations was invented or discovered, however you like to think of it, which is to say, I want to design a slide that will allow a ball to go from here to here in the shortest amount of time. What's the shape of that slide? This stumped a bunch of people, famous names, saying, oh, it's got to be the half arc of the quarter arc of a circle. It's got to be a parabola. It turns out to be none of those things. It's a really complicated shape. But the solution to this problem is what's known as the Brachistakra, shortest time. And it's some crazy kind of like, I don't know how to describe the shape. I could draw you what the shape looks like. But there's like 4 little ramps at the Boston Museum of Science where you can put balls down and race them to the bottom and see which one's going to be fastest. The answer to that problem is done by using the calculus of variations, because you can write that as a functional and then use these techniques to minimize that functional. So it's not, this math is for whenever you have a function of a variable and you need to find a minimum or a maximum. For instance, if you want to know what the largest amount of area enclosed in a single curve is, so on a flat space, again, it's simple, it's a circle. But on a curved space, it's not simple anymore. Again, you use this. In that case, you're maximizing instead of minimizing. What's the largest area? Same idea. The math is really powerful for a variety of different fields. We use it primarily to calculate the first variation, second variation, for a couple of reasons. One, it gives us the governing equations that we can solve with our computer or by hand. 2, it allows us to use approximate methods where we can do pen and paper to calculate what's going to happen to a structure. And 3, it allows us to derive the governing equations that we would use in a finite element kind of computational numerical solver. So it's really powerful. Let's take a break. We'll come back at like 10:02. If you have any questions, you can shout them out now or ask them when we get back. Either's fine. But yeah, we'll take like a 6-minute break. Okay. For those of you feeling like we may have drifted a bit too far from what feels like structural mechanics, let's use all this stuff that we've been building on to solve what I think is probably the simplest structural problem. And that looks like this. We're going to take a bar. Oops. Draw a straight line. And at the free end of this bar, we're going to pull on it. With a force P. Okay. You've solved this problem before. We solved it in mechanics of materials, but we only sort of solved it. What we did in mechanics of materials is we solved it for the displacement at the end of the bar. And I will show you how to get to that mechanics of materials solution, but also get more out of it than that. So we know that the total potential energy is just going to be equal to the strain energy minus the work being done. We know that the strain energy in stretching is EA over 2 times the integral of our strain squared. It's EA over 2 outside the integral if we assume that our modulus in our cross-sectional area doesn't vary with x. We'll assume that here. Multiplied by our strain, sorry, the integral of our strain squared dx. Note that I'm using the kind of curly epsilon here for strain. The strain in this problem is the derivative of our displacement with respect to x. How is the displacement change along the length of the beam? That's strange. Strain du dx. So this thing takes on squared dx. And for the sake of making our notation a little bit nicer, we've already introduced the idea of using u prime to denote the first derivative. This is the first derivative, so we'll write this as EA over 2 times the integral of u prime of x dx. Now, in this case, our work is really trivial. We don't have any force distributed along the length of the beam. Nothing depends on position for our work. We just have force applied at a single point. So there's no integral to be done here. We just need to say that our work is simply the force times the displacement at a point. It's the displacement u at the point W. So, yeah, good. The displacement u at a point L. I didn't tell you that it should be from 0 to L. I should do that. I should also denote that our x-axis is running this. Ooh, God. Running this way. So x is equal to 0 is at the wall. X is equal to L is at the where we're applying the force. So our force is being applied. So our displacement, the force times displacement is force times the displacement of x is equal to L. So this isn't bad. Total potential energy just becomes yeah, we can sure. 2 is the integral here, L u prime of x dx squared. Oops, I lost it over here, didn't I? Minus p times UL. Sorry, just for a correction there, I had lost the square term in my displacement here. So this one's correct. You'll notice this helps motivate why I did what I did up here. Our total potential energy that we took up here has x as our independent variable, u and u prime as our dependent variable. U because our force times the displacement enters the problem, and u prime because u prime is our measure of strain in one direction. So we already know how to calculate the first variation here. It's a little bit, that's not tricky to exercise, but let's walk through it together. So what we want to do now is we want to calculate the first variation in V. So the first variation in V, as we know, is going to be equal to the derivative of V with respect to u times du take a second and see if you can calculate what dV is, the first variation in V is. Hopefully you got something that looks like this. I'll note that because this is a strain squared, when you take the derivative with respect to strain, the 2's cancel out. And then you have to take that derivative, sorry, this derivative, and then multiply it by delta u prime. So you end up with u times delta u prime. And then in this case, this is pretty simple. This just becomes p. Then you multiply p by du. Did folks get this? I'm not seeing a lot of nodding heads. How about now? Does this make sense now that you see it? It's not that bad, right? It's just, I think people get messed up when you have to take derivatives of things that live within an integral. Just let it be. It's okay. You just can take the derivative as normal. If you want, if you're more comfortable, you could stick this term here inside the integral. Maybe that'll make it easier for you to see that you can cancel out those 2's, doesn't really matter. But what you're doing is, the way I think of the operation is, first take the derivative, multiply the result of that term with the variation. Take the derivative, multiply the result of that term with the variation. That's kind of the way I approach it. Okay. Now, depending on how well you remember what we talked about last class, you might recall that what we would like to do is we want to be able to throw away our arbitrary virtual displacements. We want to say they're arbitrary. So whatever multiplies our virtual displacements has to be equal to 0. But we recall that that's fine for here, but we have this appearance of a derivative of our virtual displacement. That's a problem. We don't actually know anything about the constraints or lack of constraints on the derivatives of our virtual displacements. So the way to resolve that is by getting rid of that derivative term. When you see a term like this, your first thought should be, I have to get rid of the derivative. And the way I get rid of this derivative is through integration by parts. Which is to say that the integral of u dv is equal to uv minus v. It's all wrong. Hold on. Minus the integral of v du. Take a second and work through the integration by parts, and be sure not to lose this term. This term, unlike the last problem, is going to be really important for us. Oh gosh, no, it's all right. That's right. I lost this, didn't I? There we go. Sorry about the confusing double use of u and v, but I feel like this is the way you learn calculus. So. Oops, did I miss something there? So I made a mistake up here. I lost the prime on my u. So this should be EA as the integral of u prime times delta u prime. Hopefully you didn't make that mistake too. If you did, I apologize. It's my fault. The result of the integration by parts, which is this is the term we're integrating by parts, should just be equal to EA times u prime times du, evaluated between at 0 and L. And we subtract off from that EA times the integral of, we have a du here, which means we have a second derivative of u times my virtual displacement u. I'm going to pause here to let you ask some questions, hopefully.
Just to make sure, the u in our situation is the u prime, right? And then the v.
Yeah, let me do that for you right now to make it more clear. So, okay. So in our problem, this is like the u in the pink for integration by parts. This is like the dv. And so that therefore, this is u, this is v, because we've now lost the prime. So we've kind of integrated v prime to get v. And then this is du. And of course, this is again v. Technically, the EA is also part of the u, but I pulled it out of the integral, so it doesn't matter. But technically, you could have kept it inside the integral, and then the EA would have been part of the, the integration by parts, the u for that one. I'm using pink to indicate like the integration by parts shorthand that you're familiar with. I apologize that the notation conflicts. Does this make more sense to folks see this now? Okay. Okay. Now we can go back and say, now I have the first variation. I'm going to explicitly write this out. And by that, I mean, I'm going to take this term. And I'm going to remind you what this term means, because it's going to be useful for us. So the first variation of our total potential energy is equal to EA times u prime. I'm going to run out of space here. Let me pull this down. EA times u prime times du at L. So this would be this term taking delta u evaluated at L minus EA u prime delta u evaluated at 0. So these two terms are from the orange term above. I'm just explicitly writing out that evaluation thing. It's going to be important, that's why I'm doing it. Okay. We can also, we have this term. What color do we have left to use as a highlighter? Let's use the light green. So now we have this term. That didn't change at all, so we just bring it back, P, and delta U at L. And then finally, we have our yellow term, which is this term, which is going to be EA integral from 0 to L of U double prime times the first variation U respect to x. Okay. This term and this term have the same variation. So we can collect them together, right? They both have delta U evaluated at L. So we'll write that down here together. EAU prime minus force then we have the second term. And then I'm going to pull the EA back inside the integral just for clarity. You'll see what I mean in 1 second. Okay. Remember early at the beginning of this lecture when we said we were familiar with the idea of a virtual displacement. Any particle that is unconstrained, we can imagine a displacement occurring to that particle. We can then calculate the virtual work corresponding to that imaginary displacement. What do we know about this term? Yeah, why?
It says 0 and then there's nothing like ain't no displacement yet.
You're so close. You're super close. You're really close.
I'm not too sure, but I know it's what it's.
Yeah, exactly. The beam is clamped at the wall. So we know that the displacement at x equals 0 has to be exactly 0. That particle is constrained there. We're not allowed to have a virtual displacement on a constrained particle, right? This is virtual displacement. We can't virtually move a particle that we know has to be exactly fixed in space. So this point here, this corresponds to this point right here. X is equal to 0, it's at the wall. We can't have a virtual displacement at the wall. This term has to be exactly 0. It's not arbitrary. It can't be arbitrary. It has to be 0. This whole term goes away. Now we're left with the same problem we had in the trajectory problem. We have an arbitrary displacement at the end, an arbitrary displacement at all points along the beam. And we know that they're not 0. There's no restrictions on them. And so therefore, in order for our first variation of our total potential energy to equal 0, which if our system's in equilibrium, it has to, then whatever multiplies our virtual displacements must be 0. Now there's two things that you can recognize here. One, this is a differential equation. So let me pull that out first. So if this, and this is kind of like A times B equals 0. If B can't be 0, A has to be 0. So therefore, EA times U double prime of X equals 0. That's the equation we have to solve to find the deflection of our beam. it's a differential equation. We also know that this term has to equal 0. But be careful, this term specifies the conditions at a point. This is for u double prime for all of x. This is for u prime at L. The reason why I said this was important is because by using calculus of variations, we've not only found the governing differential equation, we've also found one of the boundary conditions. There are two types of boundary conditions. One are called kinematic boundary conditions, which are restrictions on displacements. We know from the drawing of our problem the kinematic boundary conditions. We know that the displacement at 0 has to be 0, because we said it's claimed. That's the kinematic boundary condition. It says it places restrictions on displacements in certain directions. Kinematics, displacements. The second type of boundary condition is what's called a natural boundary condition, and it involves forces. More generally, it involves derivatives of quantities, but for the sake of simplicity here, it involves forces. This is the natural boundary condition. We didn't know it at the beginning, or at least it wasn't obvious to me what the natural boundary condition was. In general, when you use the calculus of variations to find the equation you need to solve, you not only derive the governing equation, you also get the natural boundary conditions for free as part of the calculation. Governing equation, natural boundary condition. It probably doesn't seem that exciting, but it's kind of a big deal. We just derived the equation and one of the boundary conditions as just kind of along for free. We don't even need Mathematica to solve this equation, right? So we have EA times U double prime is equal to 0. Well, that means we can even ditch the EA. So our equation becomes, oh gosh, U double prime of x equals 0. We can just integrate that twice. We're going to get u of x is equal to constant 1 times x plus constant 2, right? We know that this is a second order ordinary differential equation. It's an ordinary differential equation because our d's we're only taking derivatives with respect to one independent variable, x. It's second order because we had u double prime. If you didn't recognize that, you might recognize it now because we have two unknown constants. In order to find these two unknown constants, we need two boundary conditions. And look, we have two boundary conditions. We have the fact that the displacement at the clamped end of the beam is exactly 0. And we have the fact that the slope at the free end of the beam equals P over EA. The first condition tells us that C2 has to be 0, right? If I put in x is equal to 0, the only way that thing can be true is if C2 goes away. The second condition tells us that the displacement of my beam is going to linearly vary with x, depending on the ratio of the force to the stretching rigidity, EA. This might not look familiar, but let's do the one last step, which is to say, what's the deflection at the end of the beam? Well, the deflection at the end of the beam, we just have to put in x is equal to L. We put in x is equal to L, and I'm going to make one more notational faux pas, just for the sake of trying to remind you of something, which is to say that the deflection at the end of the beam is probably what you saw as delta in mechanics of materials. Delta equals PL over EA. Maybe this is ringing a bell. So when I said we did a little bit more, and I apologize for using delta here. This is, I'm gonna just like highlight it and say like in pink. It's not our deltas. This is like old delta. This is mechanics of materials delta. When I said we got something more by solving it this way, what we found was, if I was to plot the deflection, not deflection, I guess displacement of my beam as a function of x from 0 to L, what we found is that the displacement of my beam is going to linearly vary from 0 to a point of PL over EA at the end of the beam. So in mechanics of materials, we learned, by averaging out, we learned at this point. If you pull on a bar, the displacement is PL over EA. Now, we learned a couple of things. One, by minimizing the total potential energy, we arrive at the governing differential equation and the natural boundary condition. Generally, you know the kinematic boundary conditions, meaning you usually know, like, oh, my thing is resting on a surface, or my thing is clamped at a wall, or my thing is supported by a post. Generally, you know something about the kinematic constraints in your system. The natural constraints are not as obvious. Again, here's an example. This is not as obvious what the natural boundary conditions are, even in this really simple problem. So by using variational calculus on the total potential energy, we found the governing differential equation. We found a boundary condition. We used the governing differential equation with the natural boundary condition and the kinematic boundary condition to solve for our displacement at every point along the beam, which means, going back to what we started this lecture with, if you were to speckle this thing, speckle means like spray paint a bunch of little polka dots on here, clamp it at this end, and pull on it, what you would find is that the dots would linearly get further and further apart away from my clamped edge to the free edge. The maximum displacement will be this part, and it will linearly decrease until you get to the clamped edge, in which there'll be no displacement at all. The maximum displacement of this edge is something that we're familiar with from mechanics of materials, but now we know a bit more. We know exactly how this beam should deform at every point along its structure. To do this, it required a couple of steps. It required us to write down the total potential energy, calculate its first variation, integrate by parts, collect the virtual displacements and discard any inadmissible ones that are not allowed. You are not allowed to have a virtual displacement on a constrained point. And then the key thing is that we're not done here. What you end up with is the governing equation you want to solve and one of the boundary conditions. And then you can solve that governing equation, hopefully, to find what the actual displacement of your structure is as you've loaded it. Questions? Nothing? No questions. This is not going to be useful to you, I think, until you can practice one of these. So I'm going to give you one problem to work on for next Wednesday, due next Wednesday evening. And it's going to look, and I want it to look like this. You don't have to do step 6. I want you to go from step 1 to step 5. You don't need to solve the differential equation. So I want you to take a beam. That doesn't look like it's uniform, does it? There we go. This beam is clamped at one end, and it's going to be loaded in 2 ways. One, it's going to have a distributed force that's acting to stretch the beam. We'll call that distributed force f of x. Just for clarity, we're going to again take our origin to be here. And we're also going to have some crazy arbitrary distributed force acting to bend the beam upwards. We'll call that Q of x. Okay, I'm going to give you some hints here. One, we know that we can write strain in this problem as U prime. And we know that the stretching energy depends on the strain squared. 2, we can write curvature as approximately equal to the second derivative of W, our vertical displacement. My second hint, so this is hint 1, is that work done by distributed forces, just to remind you, is going to be like the integral of f of x times u of x you can stick these integrals together. Q of x times W of x. Oops, yeah. That's right.
Is that a plus?
That's just like an and for sans, and we'll just like and. You can stick those two things inside the same integral because they're both over x. My third hint is that you will probably find that you end up with something like this, which when you do integration by parts, will give you this, which means you have to do integration by parts multiple times. And I'll just repeat the last step, which is don't try to solve the differential equation. It'll be a pain. I think it's solvable, but I want you to get to the differential equation. We can deal with solving that if ever we need to. I think this is all you need to solve this problem. It'll give you some practice kind of going through these steps. Like they really are just kind of turn the crank type steps. But until you get comfortable with it, it's not going to feel like that. So like I want you to do one of these things when I'm not here. Any questions on anything that we did today? I'm going to just like highlight this and say, you think of this as like a proof. But the thing that I want you to know is this and this. All right, well, we're out of time. So thanks, everyone. Maybe I'll catch you on office hours later today. Otherwise, I'll see you on Thursday.